Okay, everyone. Today, this lecture is the first lecture for Chapter 4. Today, we will study the correlation coefficient. So let's go to page, page number. Okay, here. So let's go to page number 83. So then we can see the correlation and the covariance. So correlation and covariance is numerical indicator for uh, describe the dependence between two samples. So it is a well-known stochastic value that describe the degree of linearity between the two samples x and y. So this, if we have two set of datas, x i's and y i's, so then we can consider that pair of this data. Then correlation coefficient is just one value calculated by this equation. So that means we need to have sample mean for x and sample mean for y. So then x, the observed value minus sample mean times observed y value minus sample mean of y. And so we summate this value for I from I is 1 to n. So that is denominator. Okay. And denominator is denominator is a little difficult, but it is just a square error between observed sample minus sample mean. So observed sample minus sample mean square and summate them all. And here is also observed sample y minus sample mean square and summate them all and take the square root. Then we have correlation coefficient. Okay. So this is this correlation coefficient is the indicator between the dependence between x and y. So this correlation coefficient is always between -1 to 1. If this correlation coefficient R is near 0, then that means there is no linear relationship between x and y. X and y has no relationship. So actually it has no linear relationship. If R is close to 1, then these two data x and y has very strong positive relationship. And if R is close to -1, then that means these two data has strong negative relationship. Okay. In chapter 12, we will study this correlation coefficient more deeply. But in here, we would better study correlation coefficient first, and then we repeat it if we have a time at chapter 12. Correlation coefficient can be calculated by Excel using this function. So the equation is so difficult, so complex, so we can use this function for the convenience. Okay. So here is the illustration of correlation coefficient. If our x data and y data has, so x value is here, this one, then y value is that, so x value is here, then y value is here, or something like that. So then we have this graph. We have this graph, okay, this dot plot. If we have this kind of data, then that means these two x and y has very highly positive correlated. That means x is increasing, then y is increasing, so we have this direction. X is decreasing, then y is also decreasing, and we have this direction. So in this case, in the first figure, says that these two data x and y are very highly correlated. X goes up, then y goes up together. X goes down, then y goes down together. So, but in this case is different. X goes up, then y goes down, and we have this direction. X goes down, then y goes up, and we have this direction. So in this case, x and y has moves oppositely. In this case, we say that these two data has negatively correlated. So in these two cases, the first case and the second case are very highly correlated case. But the second one is negative correlative, and the first one is positively correlative. In this case, the correlation coefficient is like this. Correlation coefficient is close to 1, so plus 0.90. Then two data has this shape. And two data has this shape oppositely. Two data has this shape, then correlation coefficient is close to 1. If this two data has this shape, very highly negatively correlated, then correlation coefficient is negative and close to -1. Okay? But these two data are positively correlated, but this correlation value is not so high. So there looks like x goes up, then typically y goes up, but from time to time x goes up, but y goes down. And x goes down, but y, then typically y goes down, but from time to time x goes down, but y goes up in this case. So this case, the correlation coefficient is positive but small, not close to 1, but in 0.5. So in this case, the correlation coefficient is if the data has this shape, then correlation coefficient is positive but not so high. Oppositely, if the data has negatively correlated, but this correlation is not so strong, then we have minus 0.5 correlation. So it is far from -1. So it is in the middle between here is -1 and 1, and here is 0. Then if R is here, then data may have this shape. So if this two data has no correlation, so there's no relationship, so x goes up but y can goes up or down, x goes down but y can goes up and down, so this two data has no linear correlation, no linear relationship, so we cannot so imagine any direction of this data. So x moves up, so this event does not give any effect on the y's goes up or goes down. Then in this case, the correlation coefficient is almost 0. Okay. In this case, is also x goes up or down, but y has no direction. So then we say that in this case, correlation coefficient would be around 0. Okay. So correlation coefficient can describe the linear condition, linear relationship between x and y, and correlation coefficient is close to 1, then two data has very highly correlated. Correlation coefficient is close to -1, then two data has very highly correlated but negative correlation. And R is positive but not so high, then x and y has correlation, but it is not so strong, and it is also negative correlated, but the correlation is not so high. And if correlation coefficient is 0, then these two data has no relationship, linear relationship with each other. Covariance is very similar to correlation, but correlation is normalized, so correlation always has the value between -1 to 1, but covariance does not have that so normalized effect. So correlation is just calculated by this equation. So here the denominator is exactly same as correlation. So here correlation denominator looks like this, and covariance denominator looks like that, and these two very similar, but nominator is different. So covariance just divided by the number of samples, but correlation case is so take this equation. So covariance and correlation is a little different, but the rule is the same. Covariance is high, then high and positive, then that means two data has very highly correlated positively, and covariance is very so low, negative, then two data x and y are negative correlated, and covariance is approached to 0, then covariance is approached to the 0, then these two data has no linear dependence, so relationship. But covariance is more advanced value, and covariance is important for the portfolio optimization. Okay, so covariance is positive, then x and y tend to move the same direction as correlation, and covariance is negative, then the x and y moves the opposite direction, and x and y are uncorrelated, then covariance is 0. So this concept is popularly used in the financial portfolio analysis. So many hedge funds use this property to find the optimal portfolio. So this covariance is very important in finance. So portfolio managers can apply the concept of reducing volatility. Reducing volatility means that reducing risk. Reduce the risk of portfolio using this variance, this covariance value. So if you have a chance, then please attend my financial risk management course. If you study the financial risk management course, then you can so practically apply this covariance value to the portfolio optimization. Okay. And as you know, the correlation coefficient is values between -1 and 1. Okay. So the correlation coefficient also divided by the population correlation coefficient and sample correlation coefficient. Covariance also divided by the population covariance and sample covariance. Population covariance case, the denominator is the number of samples. But sample correlation case, the denominator is n-1. Okay, so be careful. Population correlation coefficient, population covariance is like this, and the sample covariance is like that. It is the reason why we use the n and n-1 for population and sample respectively is the same reason as we studied in the variance. So population variance and population sample variance case, we have the same fact. Okay. So population correlation coefficient is obtained by this equation. So covariance of x and y, of course it is population covariance divided by population standard deviation of x times the population standard deviation of y. So then we obtain the population correlation coefficient. Sample correlation coefficient can be obtained by the sample covariance divided by sample standard deviation of x, sample standard deviation of y. So that is sample correlation coefficient. So correlation coefficient can be calculated by this equation, or it can be calculated by this equation. But these two equations are one in the same, okay, because, okay, let's see. So correlation coefficient okay. Correlation coefficient, so correlation coefficient, I'm sorry. Wait for a moment, it is not so good. Okay. The correlation coefficient rho is, population correlation is sigma xy divided by sigma x and sigma y. So that is 1 minus n summation I is 1 to n xi minus mu x yi minus mu y, where mu x and mu y are mu x and mu y are mean of x and mean of y respectively. So divide by square root 1 over n summation I is 1 to n xi minus mu x square square root 1 over n summation I is 1 to n xi minus mu yi minus mu y square. So then that is, so here is, so square root 1 over n and square root 1 over n is, so these two value come, so go outside in the in here, then we have like this, and summation I is 1 to n xi minus mu x square, and square root summation I is 1 to n yi minus mu y square, and 1 over n summation I is 1 to n xi minus mu x yi minus mu y, and these two 1 over n is cancelled together, and we obtain the same equation as correlation coefficient. Okay. For the same reason, so R, sample correlation coefficient, can be obtained by Sxy divided by Sxsy. Okay. So it is the same. It's the same. But instead of n, we change it to n minus 1. So then it is summation xi minus x bar, yi minus y bar, and square root 1 over n minus 1 summation xi minus x bar square, and square root 1 over n minus 1 yi minus y bar square, and this n minus 1, n minus 1, n minus 1 cancel together, and then we obtain the same equation as we studied in the beginning of this lecture. Okay, so what I mean is that this equation, this represent this equation, and this equation is one in the same. Okay, so let's study the application. Suppose that we have two stocks. First stock, stock X, closing price is 41.87, 47.87, 33.26, so something like that, 37.76, 45, 45, 46, 46, something like that. They are all the closing price, daily closing price. And Y, stock Y has a closing price 9, 8, 11, 13, 9, 12, 6, 9, something like that. It is the first day closing price, second day closing price, third, fourth, fifth, sixth, seventh, eighth. So we have 8 samples for the price of stock X and price of stock Y. Okay. So then we can draw the dot plot of X and Y like this one, like this. Okay. So then first 41 and 41.86 and 9.11 would be here. So it is 41.86 and 9.11. So this one is mapped to this point, and this point would be mapped to here, and this point is 11. So here, and this point is here. This point is here, something like that. Okay. So then we obtain this two-dimensional dot plot. Two-dimensional dot plot. So then these two values would have some negatively correlated. So then let's calculate the correlation coefficient. Okay. So then the correlation population, okay, so then we would better use the Excel to calculate this correlation coefficient. Wait for a moment, please. I will open the new Excel file and we will discuss it together. Okay. So the stock X and stock Y closing price is here. Okay. So then we can calculate the sample mean like this. Average of these values, then we have sample mean. Okay. So we have a bottom line and top line. So then that is sample mean. And this one is also sample mean. Average of stock Y. So then we have a sample mean of Y. Okay. So let me change the cell property. It is not so important. Okay. First, let's calculate xi minus mean of x. So then that means this value minus this value. So this value minus this value. Okay. So then we have this sequence, and yi minus mean of y. So is also can be obtained by this value minus this value. That is mean. Okay. So we repeat it. Then we obtain the difference. And here we will multiply xi minus mean of x, yi minus mean of y. So here is xi minus mean of x times yi minus mean of y is here. So that this column is this number times this number, and repeat them all. Okay. And here is the column for xi minus mean of x squared. So that means this number squared. Okay, we repeat it 8 times. And here is yi minus mean of y squared. So this column is this number squared for every columns, for every rows. Okay, so and let's give some bottom border and to clean up the top border. I'm sorry. Bottom border. Okay. So then it is beautiful. Okay, and let's summate those values. Then this number will be the denominator of correlation coefficient. And here also sum these values, sum up those values, then we have this number. And again, sum up those values, then we have this number. Okay. So then correlation coefficient is what? This number divided by square root. Be careful, we have to take the square root of this number times square root this number. So then we obtain the correlation coefficient. Of course, the correlation coefficient is in this case minus 0.73. So that means x and y are highly negative correlated. So x moves up, then y moves down. X moves down, then y moves up relatively. Okay. And so instead of using this complex method, we can just use the one function of Excel, that correlation between array 1, array 2. Then we have the same result as we did in here. So we can use these functions already implemented in the Excel, or we can use this method, this table. Okay, I will save this file as with the number, with the name correlation example correlation, and I will upload this file on the Blackboard, so you can just enjoy this Excel file. Okay. So anyway, so then we can obtain the correlation coefficient as minus 0.7347. So so we can conclude that these two stocks are negatively correlated. So if you were portfolio manager, then you can buy this stock X and stock Y together and make a portfolio with X and Y. Then your portfolio will be very stable, because if X price goes up, then Y price goes down, and so your portfolio will be balanced. And if X price goes down, then Y price goes up, and your portfolio will be balanced. So your portfolio is very stable portfolio than X, or so it is very stable portfolio than stock Y. So you would better make a portfolio rather than have only one stock. If you have a money, then you would better divide your money for X and Y. Then your portfolio would be better than to have the stock, to have only one stock X only, or to have only one stock Y. Okay? So that is a very brief portfolio theory. Okay. And so you can calculate covariance using the function covariance. So sample covariance and sample standard deviation and correlation and so on. So again, let's do the Excel. So if you want to calculate the covariance, then you just use that covariance. So sample covariance, for example, between X, sorry, it has X, Y. So then that is covariance. And so standard deviation for X is, as you know, that we can, so sample standard deviation for X and standard deviation, sample standard deviation of y can be calculated by the standard deviation, sample standard deviation for y. So then we obtain the sample standard deviation for x, sample standard deviation for y. Correlation coefficient is again obtained by covariance, that is covariance value, divided by standard deviation of x times standard deviation of y. So then we have correlation coefficient again. This value is same as this value, or this value is same as this value. Okay? There is three ways to calculate correlation coefficient. One is very primitive way to using this table. The other is very smart way to use the correlation function given by the Excel. And the third is using this equation. So you calculate covariance and then standard deviation of x and then standard deviation of y. After then, the correlation coefficient is covariance divided by standard deviation times standard deviation. Then you can obtain the correlation coefficient. Okay, we are almost done. Let's go to the next slide. Correlation of portfolio design. Okay, so if you want to study the optimal portfolio, then please study the risk management or portfolio management in Stony Brook University College of Business. Okay, weighted mean is simple. So instead of actually sample mean is summation of, so I is 1 to n 1 to n 1 to n xi divided by n. So instead of using this sample mean, we use the weight vector, so and weight times samples and summate them together, then that is weighted mean. In this case, sum of weight should be exactly same as 1. So this weighted mean is used for used for your grading. So your instructor, Aaron Kim, might give the weight of 30% for homework, 20% for midterm exam, 40% for final exam, and 10% for the term project. Then 30%, 20%, 40%, and 10% will be 100%. And one of the students has obtained the 85 points for the homework, 68 for the midterm, 78 for the final, and 90 for the term project. Then the student score would be 30% times 85, 20% times 68, 40% times 78, 10% for 90, and 79.3. In this case, this kind of calculation is weighted mean. Weighted mean is nothing but this one. So you always use the weighted mean when you obtain the grade of some courses. Skewness and kurtosis is also very important statistic, but they are a little difficult, so we would better not study these slides, okay, in this course. But someday, if you have a chance to study some more advanced statistics, you have to study skewness and kurtosis. Okay, that's it. It is the very simple lecture for the correlation and weighted mean. So next lecture will be chapter 5. Okay, thank you very much. Have a nice day.